Hello again and welcome to Module 2 of the Microsoft Certified Azure Administrator course. This course is to prepare you for AZ-103. In this module, we're going to be taking a look at how we implement and manage Azure storage. As a Microsoft Certified Azure Administrator, you'll be expected to demonstrate a high level of competency with Azure storage technologies. That means being able to create and configure storage accounts, being able to import and export data into Azure and from Azure, being able to implement and configure Azure files and file synchronization, implementing and configuring Azure backup and recovery services. In this module, we're going to cover off those 4 objectives, and for 3 of those objectives, we're also going to cover off a lab exercise. Because of the nature of the Azure import and export data services, it's not possible for us in the labs to be able to create orders for the import and export service, because the subscriptions we have as trial administrators don't give us the rights to do that. However, what I would suggest is in your own time, take a look at configuring those services and maybe not committing the order to go through. Once we've done that, there's also going to have a short recap on some of the course administration and frequently asked questions. So to prepare you for the second objective of the exam, we're going to go through each of those sub-objectives in detail from a theory perspective. Then we're going to put you in front of some labs that will help cement those skills and turn that into knowledge and expertise. The AZ-103 exam is going to expect you to be able to demonstrate competency in each of the 4 sub-objectives of storage. We'll be revisiting this slide at the start of each module just to help you understand the overview and what each of the sub-modules is going to cover. In Objective 2, Lesson 1, we're going to take a look at the art of creating and configuring storage accounts in Azure. For the creating and configuring storage accounts sub-objective of the AZ-103 exam, we can expect questions around the following areas: creating and configuring storage accounts within the Azure portal and using the CLI and the PowerShell commandlets. Configuring network access to storage accounts, not just through the public endpoint of our storage account, which is created for us automatically, but also through connections to virtual networks in Azure to provide a private connection. We'll need to be able to demonstrate the ability to create a shared access signature that we can use to delegate temporary non-administrative access to users of our storage, and also to be able to manage access keys, which we use to provide administrative access to our storage accounts. We're also going to need to be able to install and use the Azure Storage Explorer tool, which is an add-on for the Windows operating system. It's also available for Linux and Mac that allows us to work with and experience Azure storage with a graphical user interface. Being able to monitor the activities that happen in our logs and also to monitor the performance of our logs is also a key requirement. For that, we'll be using the log analytics component of Azure Monitor. Finally, one of the big sell points of Azure storage is our ability to be able to replicate it geographically and in a way to provide high availability. So we're going to be expected to know how to handle questions that demonstrates the choices we should make in choosing the level of storage replication, how that implements price, and how that underpins service level agreements. In the AZ-900 Fundamentals course, we discovered that Microsoft Azure Storage had 2 main use cases. The first one is to provide storage that's available through a RESTful API. That's a programming interface that allows other applications that we develop or our partners develop to be able to interact with our storage through HTTP commands. To support those kind of services, which are typical for platform as a service storage solutions, Azure Storage Accounts allow us to create queue storage for storing messages, typically in transit from one application component to another. It also allows us to create table storage, which allows us to store data in a structured manner. And also as well, we have blob storage, which is effectively used for file storage for applications. Microsoft Azure Storage also provides services that lend themselves very well to infrastructure as a service workloads. Probably the most prominent of that is Azure Disk Storage. That is where we use Azure Storage blobs to keep the virtual hard drive files that we mount to our virtual machines in Azure and use as if they were physical hard disks in those machines. In addition to that, Azure also provides what we call file storage. That's where we create a storage blob, but we complement that with a software as a service SMB mount point that acts in many ways like a file server as a service. Now, it's important to remember that there are some subtle differences in the way that Azure file storage works between a file share on a Windows server. However, the end functionality that it provides in the ability to be able to map a network drive from a Windows client or server to the storage account and to be able to browse it through the Windows Explorer utility of our operating system is pretty much the same. In the exam, we're going to need to be able to create and configure storage accounts, and we'll need to be able to do that using 4 different methods. The first method, which I'll discuss here in the theory module, is to use the Azure portal. All you need to do here is log into the portal and authenticate, and provided you're a member of a role that has the ability to do so, you can create a storage account. Once that storage account is created, we then see the screen on the right hand side of this PowerPoint slide. As you can see, our storage accounts have several mandatory fields. So for example, our storage account should be, or in fact must be, a member of a resource group to keep it organized and structured, but also to allow us to delegate administrative access to the storage account object within the Azure portal. Now, it's important to remember that when you look in the Azure portal and you look at the access control, open brackets, IAM, close brackets tab, what you're going to see is that people have access to the administrative object that represents that storage account. That doesn't necessarily mean that those people have any access to the files held within. What that means is they can configure and make changes to the storage account object. So an example of some of the activities that somebody who is a member of the role that has the ability to create within that storage account, we could create containers, also known as services. As I mentioned previously, Azure storage accounts support 4 service types: blob storage for keeping files for our applications, file shares for keeping files used typically by human beings that are accessed over the SMB protocol, like a file share, table storage, which is where our applications use semi-structured storage to keep values in, and also queues for them to keep messages, typically when they're being moved between one application and another. The other attributes that our storage account must have is it must have a location. What that means is our storage account has to be based in a particular geographical area. However, we can use the replication options available to provide locally resilient storage, globally resilient storage, or zone resilient storage in one of 4 ways. A storage account also is based around a performance tier. So for example, in this one here, I've just created this storage account based on the standard tier. Now, when you get into the labs, you'll get a chance to create storage accounts using the different performance tiers. And what you're going to see as you move up to the premium storage tier, where performance becomes faster, we're going to lose the ability to do certain things like geographic replication. And that's because if we want the storage solution to primarily perform really quickly, we're not going to be able to accommodate certain replication scenarios that introduce a level of latency into the performance. As you can see by looking at the tabs available within the storage account, just like any other resource like a virtual machine, we have an activity log that tells us what administrative changes have been made to the object for the storage account in the Azure Management Portal. So for example, if somebody has created a container, deleted some storage, or done something to it, here's where we can go to have a look and see who has done what and when. We can also apply tags to our storage account. Just like virtual machines and resource groups, it's very important to label our storage accounts with tags so we know how to manage them and who to contact if we need to do things to them. One of the things we'll come to a bit later on in this module is we'll take a look at access keys, shared access signatures, firewalls, and network configuration. Also towards the end of the module, we're going to take a look at the metrics and locks functionality that's applied to storage accounts as well. Creating a storage account in the Azure portal is a very straightforward activity. You go into the portal, you click on the new button, and you add a storage account. It's quite simple then. All you really need to do at creation is just choose which location it's at, which resource group it's going to be contained in, and its performance tier and replication capabilities. That will potentially modify the services that we can create and host in that storage account. In the exam, we're also going to be able to be able to demonstrate that we have some level of knowledge using Azure PowerShell, the command line interface, and the Azure Storage Explorer to be able to create and configure storage accounts. So when you get into the labs, there's going to be a one lab exercise for each one of those scenarios. It's really important that you complete that. Whilst it's unlikely in the exam for AZ-103, in the simulation exam component, it's unlikely you would get a question that asks you to create a storage account from PowerShell. Most of the tasks asked you in the exam are driven through the portal. However, it's entirely likely you might come across a multiple choice question that tests your use of the correct commandlet for either the PowerShell or the command line interface to create some storage. So when you're moving those labs, please pay attention. It's important to remember that primarily Azure Storage is used for applications storing information that they access through an API. That means they send commands to that storage account using HTTP commands to create, read, update, and delete objects in our storage containers. That does have a slight downside to it, which is, unlike a file share, it's very difficult for a human being to go in there and either do some testing or some diagnostics work in that storage account unless they understand what the HTTP commands are. So, in order that you as a systems administrator don't need to know how to be able to create those commands in something like Visual Studio or an ASP.NET application, just to test and conceptualize Azure Storage, Microsoft have created the Azure Storage Explorer utility. It's available as a free download from Microsoft's website. You install it on your client computer. There are options to install the Azure Storage Explorer on both Windows, Mac OS, and Linux. When we install the Storage Explorer, we're then able to log in and authenticate against our Azure subscription. That'll then return a list of the storage subscriptions that we have access to. We can then browse into each of those containers, or we can add additional storage accounts in by adding a URL and a key to be able to access that. We can then browse the contents of those containers graphically. That means we can see a graphical representation of what's stored in our blob containers in terms of files. We can also see what's in our file shares, including the directories that are created underneath there, and browse them a lot like we would a normal Windows file share. We can also view the contents of queue and table storage. So if we're trying to do some testing where maybe we need to create a test message, we can use the Storage Explorer to create that content. Also as well, we can use this as a mechanism of populating data into tables using a graphical user interface. It's really important though that we don't confuse the Microsoft Azure Storage Explorer with a very similar tool called the Azure Storage Emulator. The Azure Storage Emulator is a component of Visual Studio that you install on your local client computer. The idea being with the storage emulator is you can create on your local hard drive storage that pretends, or rather emulates, to act like an Azure storage account, so you can test out and develop your solutions on your local machine. However, the Azure Storage Explorer is there for allow you to explore, see the configuration, and put configuration into the actual files themselves. So for the exam, please take care not to confuse the Storage Explorer with the Storage Emulator. Regardless of our attitudes towards enterprise computing, cloud applications are designed to make components available over the internet. That means we can have loosely coupled systems maybe hosted in different cloud providers, different data centers, or different geographical regions that communicate securely over the public internet. That means the typical types of authentication and file transfer protocols that we use don't lend themselves very well to these kind of disconnected applications in the cloud. So, Azure Storage gives us the ability to use two forms of authentication to be able to get access to storage accounts. The first option is to use a SAS token. SAS stands for Single Access Session. What that means is SAS tokens are time constrained. When you create a token that allows access, you're basically timestamping it with a start time and an end time. That's pretty ideal if we're giving access to an external user to, say, a file that contains a video, some music, some sound files, or even just images for a short, constrained period of time. We're able to use SAS tokens to provide quite granular levels of access to individual containers or blob objects in those container objects. So we can become quite restricted using a SAS token into what that user can access. Generally speaking, we use a SAS token for user access, typically through an application that we've developed. The alternative to a SAS token is an account key. Account keys are designed to provide persistent access to a storage account. Unlike a SAS token where the access we provide is quite granular, an account key is quite generic. So if I'm given the key to the storage account, I have total access to everything that's in that storage account. All containers, all objects. Generally speaking, what we do is we use this to provide a way of persistent form of access for our applications, and occasionally to our software developers or administrators who need to be able to create the content published into the storage account. One of the important things about account keys is it's essentially a very long and very complex password. If that account key becomes compromised and somebody that shouldn't have access to it has it, they can use that account key in conjunction with the URL of the storage account to be able to access that information. Now that's obviously not desirable. What we would do there in those circumstances is to change the key. The problem with that is, though, when we change that key, the legitimate users that use that key to access the storage will then lose access until they identify a new key to use. So we need a solution that helps with that. What we do in Azure is to create a pair of keys, a primary and a secondary key. We generally speaking issue both keys to application developers, and when they're developing application components that integrate and use the Azure storage account to get information, they'll give it a primary key and a secondary key to use as a failback option. That's quite good, because if one or both of our keys does become compromised and it's available to an attacker to get our information, we can first of all reset our primary key. What will happen then is when applications come in and attempt to authenticate using the primary key, they'll see that primary key is no longer valid. They'll attempt to authenticate using the secondary key. When they have the secondary key, they can gain access and use that as a mechanism to obtain the updated primary key. We generally give 24 to 48 hours notice, then we will reset the secondary key again. What that means is the account keys at that point are not what they used to be, and we've not necessarily blocked anybody's or any application's access to that data. The Azure portal makes it quite easy for us to generate shared access signatures and access keys. We use the Azure portal to do that. So what we need to do is log on to our Azure portal, connect to the storage account we want to grant somebody access to, then we go to the settings pane of the blade. Here we can access shared access signatures and the access keys. We use access keys and single access signature tokens to be able to allow people to get access to the contents of the files. It's very important that we appreciate there's a difference between being able to connect to a container, read, delete, update, or modify the objects that are in there, as opposed to having administrative access to the storage account itself. That's why, in addition to the access keys and shared access panes in the management control, you'll also see one called access control. Access control is where we make Azure administrators or developers a member of the owners, contributors, or readers group for the administrative object. Now, just because I have access to the administrative object that contains the configuration of the storage account does not necessarily mean to say that I have the ability to gain access to the storage itself. So, when we're creating a SAS token, what we need to be able to do is click on the SAS management blade, and in there we can determine the level of granularity that that access token is going to provide. Does it provide it to the entire storage subscription? Does it provide it to a particular container, or are we providing access to individual granular objects? You can see in the dialog box we're also able to grant levels of permissions. It's entirely possible that we may want external users of our applications just to be able to read or to process a file and not necessarily be able to update it and change it. One of the important things to see in there is the list attribute in the permissions. What that means is we can grant whether or not people with a SAS token can look at the contents of a container and actually identify which files are there. That's quite useful in external application scenarios, because what we may do is just give people access to particular files and we tell the application where that file is. By doing so, the end user or the person with that SAS token isn't able to come in and browse our directory structure and look at the other files that are in there. That's quite important for separating out roles and responsibilities. SAS tokens are temporary, so a SAS token will have a start time and an end time associated with that. Now, we're able to make that expiry time access period last as long as we like. However, it's considered good practice to obviously have that only available for the period of time that's required. It's also possible for us to whitelist particular IP addresses that can use the SAS token to access the storage. Unlike a firewall, what we're doing here is we're saying that only certain IP addresses will be considered as being able to use that SAS token. That's quite useful because if our SAS token becomes compromised, potentially people can access the data. But if we only allow certain IP addresses to use this particular signature, what we're able to do is very tightly associate a SAS token to a user or an application or a particular network. That's quite important for defense and depth purposes. Unless we're coming from the right IP address, then we're not going to be able to use this SAS token to authenticate. SAS tokens allow us to access storage using two protocols, HTTPS, which is encrypted, and standard HTTP. Now, it could be that we should only ever be using HTTPS to access this data. That will ensure it's encrypted in transit. However, potentially, maybe we're integrating with a legacy application or legacy browsers for some reason that can't handle that level of encryption, and perhaps we need to allow people to be able to access the storage just using HTTP. Our default is to require HTTP access here, but it's entirely possible we may run into scenarios where we have our arms twisted that we have to allow access to unsecured HTTP connections which are not encrypted. When we transfer information over HTTPS, it is encrypted, and we use a signing key to do that. The idea being there is that signing key encrypts the data whilst it's in transit. Pairs of keys are then issued down to the client for them to be able to decrypt the data when it's received. Towards the bottom of this dialog box, we can see the key bits of information that we need to be able to locate and access our storage account or the objects that we've been given granted access to. The SAS token itself is essentially a token that says from when do I get access until when, and when does my access expire. What is the token itself? What is the complex password I'm going to use to be able to access this information? Then finally, we also have the blob service SAS URL. That includes the fully qualified DNS name of our storage account for public connectivity. As you can see here, when you look at the URL that's been generated by Azure DNS for us, we're using a set namespace. So when we create our storage account, we have to give it a globally unique name. In this case, GSC copy SA is the name of our storage account. .blob.core.windows.net is the standard DNS URL for that it publishes the IP address against for that service. There's two things we need to take away from that. Obviously, our storage account name needs to be unique within that service name. However, the other thing to remember as well is we can always provide an alias for this over public DNS to provide something that's maybe easier for people to remember than a standard DNS URL. Also, as well as providing an access URL for people to be able to access the blob storage, which generally speaking would be happening through a web browser or through a web-enabled application communicating with APIs. We also see the URL for the file service. That's the location of the SMB mount point that if we were mapping a drive or using some kind of SMB explorer like Windows File Services to be able to map to or browse to a location, that's the path we'd use to connect there. Imagine somebody gave you the keys to a safe. You'd then be able to open up that safe, put into it whatever you want it and lock it, or open up that safe and remove whatever you want from it. This is why we call management access keys keys. The idea is if I have the key to the safe, I have complete access to the safe. What I can't do with the key though is change the location of the safe. That's what I need to be a member of an administrative role for using the access controls module within Azure. However, if I've been given the key to the safe, I can open it up and put in there whatever I want and remove from it whatever I want. I'm free to do whatever I want within that safe because I have the keys. So if I give people the key, I'm basically giving them a very long, very complex password that they can use in conjunction with the URL of the storage account to be able to have blanket access to it. We issue access keys very sparingly because if I've got the key to that access to that container, or I've got the key, to the storage account, I get full, unblown administrative right access to it from the files perspective. Access keys are issued on a storage account by account basis. Unlike a SAS token where I can granularly grant access to individual files or to a container, I can use access keys. When I give somebody an access key, they get rights to everything in that container and they can access it. One of the things we can also do as well, alongside using SAS tokens and management keys, we can apply a storage policy which says whether external access is read-only or read-write execute delete. So we can overwrite the ability of people to externally be able to create files in there and to delete contents in there. Just because we've chosen to keep our data in Azure in the cloud doesn't mean that information isn't confidential. You have to bear in mind that yes, although we do by default create a public endpoint where people from the public internet could connect to our storage from with a storage account, we can also disable that public endpoint and only allow access to our storage from a virtual network, either within Azure or by extending that virtual network back to our on-premises environment. So, because our information may be confidential, it's very important that we're able to implement activity logging. Now, activity logging can be configured under the monitoring section of the management blade for a storage account. There's a box in there called diagnostic settings. Now, if you visit in there, what you'll see towards the bottom of that dialog box is our ability to turn on and off read, write, delete, and delete data logging events. What that means is if I enable read logging, every time a user comes along and reads a particular bit of information from either a blob or from a file, a record will be created in the audit logs. That will allow us to go back over time and see who has used our information. If something has been deleted or overwritten, who has done that. We're able to apply policies around monitoring quite granularly in the storage account. The first thing to remember is these monitoring settings are specific to one storage account. The other thing that's important to note as well is we're able to disable storage monitoring by clicking the off button at the top, and also as well we can have more granular settings and put in place for file, table and queue storage. Retention of our audit logs is quite an important consideration. It may be that we don't fall under any regulation, but it still might be important that we say that we keep our access logs for maybe 30 days or a month. Now, by default, the monitoring policy will keep audit data for a period of 7 days. By default within Azure, we get 30 days of audit data for free. If we want to extend auditing, the audit log retention period for longer than that, we can always increase that number of days to whatever value we want. However, that comes at a price. Any storage that we use in excess of those 30 days, we need to pay for that extra storage. However, that cost is not very significant. The other thing we're configuring in this page as well is our performance monitoring. Metrics are the way of looking at how frequently a file was accessed or how frequently a table was queried, for example. So we're able to see performance-related information. It's important to remember that logging is about access. Performance metrics are about performance. One of the things we do in Azure is we aggregate data. Now we've got per minute metrics and per hour metrics. The idea is per minute metrics are useful for granular troubleshooting and trying to understand much more in detail over a shorter period of time. Hourly metrics, what we do is we take an average of the value over the hour-long period. That means that data can be stored for much longer and consume a much smaller amount of information. It's not uncommon to have a monitoring policy in place that, yes, we enable API metrics and delete data metrics, both on an hourly and minute-wide basis. But what we probably only do is keep the 1 minute level of metrics for a short period of time, maybe for the last day, the last week, or the last month. Then we'd retain our hourly metrics for a longer period of time. Perhaps that might be for as long as a full year. The idea being is we can have a look at historical trends in performance. Because audit logs will tell us about anomalous behavior, and because performance logs will tell us about anomalous performance of the storage, it's very important that we can react to that information. Our mechanism of doing that contains two parts in Azure. We have the idea of creating an alert. A rule is applied to our storage account that says when certain things happen in our storage account, we're going to undertake a notification or some action to fix this scenario. So what we can do, for example, on a particular storage account is alert on metrics. If the performance on the storage or the workload on storage gets too high and it gets close to the limitations of the storage account, we can create an alert that would trigger a notification being sent either by email or by text message, or using a webhook, which is how monitoring tools talk to one another, to send them to another monitoring tool or another systems management tool. We can also configure the alert to take some kind of diagnostic or self-heal action for us. What we can do is create a logic app in Azure that just contains a workflow of a sequence of events. For example, that workflow events might be to trigger a full copy of our data to another region, and then to change the external load balances, or to change the public DNS records to tell our users to access that information from another region. So actions allow us to implement logic apps that configure self-heal information. Azure provides us with 4 options for storage replication. At the cheapest tier, we have locally resilient storage. What that means is even the cheapest amounts of storage in Azure, our data is written to a minimum of 3 hard disks. With locally resilient storage, all of those replicas live within the same data center or the same facility. What that does do, though, is quite nicely protect against disk failures and storage appliance failures. From a performance perspective, the storage acknowledges that data has been committed to disk once the information has been received by all 3 hard drives. That means in a failure scenario, we're not going to have any risks of data loss. Now, because all 3 disks live within the same data center, there's very little latency between them. So that means there's very minimal performance impact for data latency. The next most expensive tier of storage replication is zone replication storage. What that means is within one geographical region, we replicate this data out across 3 zones, typically 3 data center buildings. What that means is because of the way Azure is architected, each of those buildings has independent supplies of power, electricity, network connectivity, and air conditioning. That means our data can survive the loss of 3 individual data center buildings within a single region. So, because each of those zones exists within the same geographical region, we can be confident that none of our data has left a geographical region. If we've created zone resilient storage in UK South, our data will never leave UK South. Now, there are some scenarios where we need to provide a higher level of survivability for our data, and this is where geo-resilient storage comes into play. Geo-resilient storage is a bit more expensive because not only does it use wide area network traffic within Azure to replicate our storage from a primary region to a secondary region, it also adds more disks into the equation for us. However, it does provide a higher level of protection. By using geo-resilient storage, I can survive the loss of an entire Azure region, and my data will still be available to me in the secondary region. This is one of the reasons why in Azure we have regional pairs of data centers. So in the UK, for example, we have UK South, which is located in Reading, and UK West, which is located in Cardiff. The idea is there's a significant enough distance between those two facilities, meaning that a fairly severe political or physical disaster is unlikely to take out both buildings, so our data would persist. One of the things to watch out for with geo-resilient storage is it would be very difficult for us to be able to say that our data is tracked as being committed to disk when it's being committed to all the disks in the primary region and in the secondary region. For that reason, Microsoft's done something very clever to keep the system performing well and protect against data loss. In geo-resilient storage, the storage sees our data as having been committed to disk when it's been written to all three replicas in the primary region. It may take a little bit of time for that data to replicate out to the secondary region, typically because there's at least 300 miles between regions in Azure, and that distance causes time delays on the network. So what we do is we treat the replication of data from the primary region to the secondary region as asynchronous. What that means is the storage sees that the write to the disk or the read from the disk is being committed when it's written in the primary data center. Microsoft provides some caching technologies, so when that information is replicated over their wide area network, they can protect against data loss. So the commitment Microsoft is making is there could be latency in the data in the secondary data center, but they are guaranteeing to get any data that's written into the primary replicated to the secondary data center eventually. Finally, the last option for storage replication is read access. What we have here is a system where our data primarily lives in our primary region and there is a replica of it in our secondary region. What we allow though in the circumstance of read access GRS is the ability for our users and applications to be able to read from the information in the secondary region. That means I can use geo-resilient storage as a way of replicating my data around the world to speed up access from different geographical regions. Now, I can choose to deploy my information in, say, UK South and UK West and keep it within the same region, but I can also use GRS and RA-GRS to select additional replicas in other locations around the world. So yes, I may want to restrict my data from only living in one data sovereignty area, but I can also choose to allow it to replicate to other geographical regions, meaning I can use this as a way to provide faster read access to my data around the world. Cloud-based storage is designed primarily to be accessible over the public internet. However, it's not the way we want our storage to be accessed in all circumstances. For example, let's suppose we've created a storage account that really should only be accessed by our applications. So, under those circumstances, we might wish to disable the public endpoint to our storage account, meaning our storage account doesn't provide any external access to the services, to the storage containers that are contained within it. That means if we want to be able to access the data in that storage account, we would need to connect to it through an Azure virtual network. Now, the way we do that is by creating on the storage account something called a service endpoint. Now, that's a two-way operation. First of all, we need to configure the storage account to support service endpoints. Then secondly, we need to configure our virtual network to also support service endpoints specifically for Azure storage accounts. Now, there's a misconception that a storage account will provide an IP address for the storage account on a virtual network. That's not true. What we're doing with the service endpoint though is creating like a public endpoint for the service, but the people that can access that need to be on an Azure virtual network. So we're not joining our storage account to our virtual network, but we are allowing a private connection to that service account over Azure's internal networking. If we have a site-to-site VPN or an express route circuit, people that are on premises that can access that, provided our virtual network allows us to route through from on-premises into the VNet and through the VNet to be able to access that service. In the labs, you're going to need to be able to go in and create a service endpoint for a storage account and for a SQL database. The idea being there is what we're doing is allowing virtual machines to be able to access information that's being held in a SQL PaaS instance or an Azure storage account instance that's not exposed over the public internet. It's only available on a private network. One of the reasons why the new generation of Azure exams have been regarded as a huge success, not just by Microsoft, but by partners and certified professionals and the industry in general, is because we're finally validating experience by doing hands-on tasks in the Azure portal as part of the certification experience. When you get into the AZ-103 exam, you're very likely to run across exam simulation questions that will require you to go into the Azure browser and to be able to undertake several tasks identified within the portal. So, this first lab we're going to do under Objective 2 will have us going through several exercises that have us create and configure storage accounts in Azure. Lab 2A will focus on having you implement and configure storage accounts. We're going to do that first of all using the Azure portal. Then we're going to have you do that using the Azure Storage Explorer utility. Then we're going to have you use scripts in PowerShell and the Azure command line interface to create and configure storage accounts. One of the exam objectives that we need to be aware of as well is the ability to implement and integrate content delivery networks with our storage accounts to provide a form of caching of content to make replication easier on a global scale. So, take a break now, get in and do this lab. The second lesson under Objective 2 is about importing and exporting data into and from Azure. As a Microsoft Certified Azure Administrator, you're going to be expected to be able to handle several data import and export scenarios. This is where we're taking information either from another cloud service provider like Amazon, from an on-premises data center, from a hard drive someplace, and be able to make that data arrive into Azure. There are a couple of tools we need to be understanding of and potentially proficient with within Azure to help with that. The first is an Azure data export job. What that allows us to do is ship some SATA 3 hard drives to Microsoft and have the engineers of Azure copy data from a storage account or a particular container onto those disks, encrypted and shipped back to us. We also have the import job as well. There, what we do is we take some data from our hard drives and on-prem or in another data center or another cloud provider, copy that information onto SATA 3 disks, have a bonded courier collect those disks which are encrypted, take them to Azure, and then the engineers at Azure will present the contents of those disks to us from a storage account of our choosing. Microsoft have recently implemented a more heavyweight version of the import-export service. This is called Azure Databooks. What Microsoft have done is they've sat down with a hardware partner and created a specific appliance that's designed to store up to 80 terabytes of data and provide a very heavy encryption capability and a fast throughput experience. Then we need to be aware of how to configure and use Azure storage blobs and to be able to deploy and configure content delivery network endpoints to speed up the performance of our storage in geographical regions. Normally when we're copying information into Azure, we'll use tools like Azure Site Recovery Manager, the Azure SQL Data Migration Tool, or just Azure Storage Explorer or the AZ Copy utility to copy information over a network into a storage account. However, there are some circumstances where we might need to use the import and export tools. So for example, if we're trying to move large amounts of data very quickly into Azure, and we don't want to incur huge amounts of data ingress costs, it may be cheaper for us to copy that information to disk and move it in or out of Azure using removable disk media. Potentially, maybe we've got a lot of information that we need to send to lots of places around the world. So import and export gives us an option to be able to move that data around. Now, depending on our network performance, it may be faster to commit that data to disk and have it shipped by a courier into Azure. It's entirely possible we might want to use an import and export job to take backups of on-premises virtual machines and data and use that to ship it into Azure. That's very common in hostile data center scenarios. Also as well, maybe we're doing this for data recovery purposes. Perhaps we've lost a physical data center and we need to take the data that we've recovered from there, send it into Azure, because we're going to look at Azure as being our new recovery data center. And finally, a hostile data center. That's where maybe we're using a third party's data center environment and we're paying them for the service. Understandably, they're not going to be too happy if we want to disconnect that service and stop paying for them. Quite often, many service providers, DXC included, can make it quite difficult for users to get their information out of their data center. That's because maybe they've put some restrictions in place on who can access virtualization technologies. Maybe they're preventing connections to the internet for servers as well. So, in some cases, we may have no opportunity but to use media and the import and export jobs to get information out of a data center and into Azure. Azure Export allows us to get data that's already in Azure and ship it back to us on-prem using hard drives that we own. The process begins by a systems administrator going into the Azure portal and creating a data export job. Doing that job, we're tagging the storage accounts and containers of data that we need to get committed to disk and shipped out of Azure. Then, what we do is we work with a courier to send some hard drives that we own to Azure. Those disks are taken and shipped to the Azure data center. They need to follow certain standards. For example, they need to be SATA 3 drives. Those drives then get connected to Azure by the engineers in Microsoft, and they will then copy the data that's in that storage account to those disks for us. A special utility is used to encrypt the data on those disks. That can be done using BitLocker, and it can also just be done with specific keys that are made available to us through the Azure portal when we come to decrypt the data. The hard drives get processed at the data center. The information is written to them and is then sent back out to us. It's encrypted using BitLocker, and it's then sent back to us to on-prem. At that point, we unpack them, we connect the data hard drives to whatever infrastructure we want to copy the data to. One of the important things to remember with Azure import and export jobs is we're using media that we own. There may be circumstances where we're not allowed to use media owned by a third party. Perhaps there are some concerns that may be able to recreate that information. So, the 4 states of an Azure export job are creating the job, shipping, transferring, packaging, and the job is complete. The opposite of an export job is a data import job. It follows a similar process. However, there are some subtle differences between an export job and an import job that you should be aware of for the exam. Again, with an import job, we are providing the media. We're providing the SATA 3 hard drives that data will be copied to. During the creating job stage of the import job, we as an Azure administrator go into the Azure portal. We prepare the hard drives that we're going to use using the import-export client tool that allows us to encrypt the entire drive with BitLocker. We then as a customer then create an import job using the Azure portal, which is essentially a request and a series of information for shipping details to be sent out to us and for the disks to be shipped to site. During the shipping phase, we get the disks and we put them into the box that's sent to us by the courier, and we ship that information to the data center. The shipping phase is considered complete once the disks have been taken by Microsoft, connected up to the Azure storage utilities, and are then transferred. The contents of those disks are then being transferred onto a storage account for us. That's known as the transferring stage. At that point, because we're using an import or an export job, the hard drives physically belong to us. What happens then is Microsoft's engineers then package up those hard drives and return them to us by courier. The idea then is that we retain possession of those disks. So we're then responsible for keeping those disks secure. And that means that because the disks remain in our possession, somebody can't come back and try and use a recovery utility to forensically analyze the contents of that data. Then, finally, the hard drives get shipped back to us, and that's the end of the process. With both Azure import and export jobs, there are some security considerations to bear in mind. First of all, who owns the drive? Who has the drives when the job is finished? It's entirely possible to be able to use recovery tools to look at our data and recover the data back if the disks fall into the wrong hands, either after disposal or at the time of processing. So, drive encryption is really important to us. The data on a drive that we ship using the import and export service can be used with BitLocker drive encryption. That encryption protects the data whilst it's in transit. For import jobs, we can encrypt our drive in one of two ways. We use the WAI import-export tool to be able to prepare the drive, and we can use the dataset.csv file to specify if we're going to use a file of our own creation or use BitLocker with the recovery key stored in Azure AD. For export jobs, after our data is copied to the drives, the people at Microsoft will then encrypt the drive using BitLocker before sending it back to us. Under the export scenario, the encryption key that we use to decrypt the data, we download that from the Azure portal. Azure import and export is quite powerful. However, there may be circumstances where we don't want to have to make an investment in additional hard drives just for an import and export service. So, Microsoft have done a bit of innovative work with a hardware partner to create the Azure Data Box. Azure Data Box appliances allow us to transfer information to it using a 1 gigabit or a 10 gigabit per second network interface. Each appliance can hold up to 80 terabytes of data, and it is possible to have multiple devices sent to us. From a security perspective, each data box has built-in security precautions for device, data, and the service itself. These include not only authentication and encryption, but they also include tampering countermeasures as well. Azure Data Box provide quite a ruggedized and secure tamper-resistant hardware platform. That means if somebody plays around with the appliance, we're going to know about it. If the box gets damaged or is exposed to magnetic or heat, it'll protect our data physically. The data that we keep on a data box is secured using an AES 256-bit encryption key. That means there's a very, very strong level of encryption put in place to that data at all times. The device can only be unlocked when we use a very complex password that's provided to us by the Azure portal. So, the person that created the job for the data box job needs to be the one who accesses the portal to get that key back. Once our data has been uploaded into Azure, the disks in the Azure Data Box appliance are securely wiped, and it's done in accordance with NIST standards 800-88R1. That means there's a secure wipe of that data doing, and it's very, very, very unlikely somebody would be able to recover that data by just doing forensic analysis of the drive. Just as Azure import and export services have phases that we can use to track the process of the order moving data into or out of Azure for us, the Azure Data Box service also has phases as well. That starts off with the order phase, where we as an administrator go into the Azure portal and create the request for an Azure Data Box to be sent to us with data on or for us to data put back. During the receive phase, this is when we configure and prepare that drive to get the data put onto it. During the copy data phase, the information is written to the drive. The return phase, the device is shipped either to Azure or from Azure to our environment. And then finally, the upload phase considers the data being copied from the drive to whatever source, whatever final destination of information we want that to live on. Now that could be Azure storage, it could be storage in another cloud provider, or it could be we're just copying it to local hard drives. But we're in charge of this process. Specifically for the AZ-103 exam, there are two user interfaces we need to be aware of that relate to Azure Data Box. The first one is built into the Azure portal. This is the Data Box service interface. This allows us to come along and create a request for a Data Box appliance to ship some data for us, but it also is where we come along and see the status of our job as it moves through processed, delivered, received, and data copy levels. This is also where we'll come to view our device details and to be able to obtain the passwords and recovery keys for it. There is also a user interface that resides on the Azure Data Box itself. This GUI is where we actually configure the network cards of the appliance to be able to connect to our networks and to be able to get access to the information we need it to. We can also use it to undertake the collect and copy data job, and also to prepare the device for shipping either to Azure or back to us from Azure. Another mechanism we can use for importing and exporting data from Azure is to create an Azure blob storage container. Obviously, blob storage is designed for serving images or documents directly to a browser, but also for storing files for distributed access. We can use them to stream video and audio information, write logs to. We can use them to store backup and recovery and DR data for our workloads. And also as well, we can use them to store virtual machines for Azure hard drives, Azure virtual hard drives. What this means is we can use the storage blob with a public container as a mechanism of copying information into and out of our storage account. That's really handy if we're trying to do a very primitive type of migration to Azure, where we're moving data, not necessarily virtual machines. There is a structure of data, kind of a hierarchy, that we must understand when working with blob or any other type of container within Azure storage account. First of all, we have the account object. That's a container level object at the top of our hierarchy. The account deals with who has access to it, how it's configured, and how it's replicated in Azure. Within the account, we have several containers. Whenever we create a different type of service, like a file service or a blob service, we create multiple containers. It's also possible to create named containers based on a particular type. So it's possible for me to come along and create blob containers that store my pictures, my movies, my audio files, or my audio books, for example. Then each one of those containers becomes a bit like a folder on a hard drive. It's an organization boundary, but it also allows me to implement role access controls using shared access signatures that determine what types of files and content people can get access to. Finally, within our containers, we actually have our blob objects themselves. When you consider often, this might just be what we call a file. So we could have a blob object, which is a JPEG file or a movie file. It's just a sequence of binary large objects. The fact that it happens to be a file is neither here nor there from the storage's perspective. Azure Blob Storage allows us to create three types of blob. We have block blobs that are used to store binary data and text data. We can store up to 4.7 terabytes of data in block blob storage. Block blobs are made up of blocks of data that can be managed individually. The opposite to a block blob is a page blob. Page blobs use random access storage to be able to store files. Page blobs allow us to keep up to 8 terabytes of data in an individual container. Page blobs store virtual hard drives that we use for Azure virtual machines and also serve as the virtual disks for virtual machines. Finally, the third type we have is an append blob. What we can do with an append blob is we create an additional block blob, but it's optimized for append storages. The idea around an append blob is if I come along and I create, say, a virtual hard drive file that's currently 2 terabytes in size, and I need to resize that drive so that it's 3.5 terabytes in size, I can use an append blob to add that extra capacity to that existing blob. As we've discussed previously, blob storage is designed to be communicated with over an API, where CRUD commands, sent over RESTful commands, are used to upload, read, delete, and modify objects that are in Azure. So we've got to work with some kind of middle tier of software to be able to do that. So we've got some utilities that will help with this. First of all is the AZ-copy command. It's a Windows and Linux command line that allows us to be able to copy files in a similar manner to the way the robocopy command in Windows works. Then we have the Azure Storage Data Movement Library. Essentially what that is that's a library of commands that we can add into our Azure projects to allow them to be able to use the capabilities of AZ-copy from within our software. That would mean that our applications we write, we can use .NET to write code to have it interact with storage accounts using the AZ copy utilities. Azure Data Factory is some specialized functionality in Azure Storage Account that makes it optimized for storing huge amounts of information that's being used to keep information about large data scenarios. It's optimized for analyzing the data as it's being committed to it and for handling huge amounts of information coming through. We have the Blob Fuse Sharp virtual driver. What we can use that for is to allow access through the Linux file system to our storage. The Azure Databox service and the Azure Import-Export service are also ways of getting information into blob storage and out of it as well. During the previous labs, I had you create a content delivery network with content delivery endpoints. Now it's time to understand exactly what a content delivery network is. Conceptually speaking, if you come from an infrastructure background, a content delivery network is a lot like providing a WAF connection. That is where we have an appliance type storage in different locations that will cache certain types of content locally. So, a content delivery network is a distributed network of servers that can efficiently deliver web content to users. So for example, we may have a web application in several regions around the world, but all the web application itself does is provide people a location on our content delivery network or in our storage of where web files such as web pages, video files and images might be held. Content delivery networks store cached content on the edge servers in point of presence locations. The idea is if our point of presence location is close to where our users are, they will have minimum latency accessing the content of our application. Content delivery networks often develop as a global solution for rapidly delivering high bandwidth content to users by caching that content at strategically positioned nodes around the world. Try and think of what Microsoft does with TechNet videos. They create fairly large video files and they want them available around the world nice and quickly. So they use content delivery networks to make sure that copies of those video files are available close to where you are as an end user. Azure Content Delivery Networks can also be used to accelerate dynamic content which can't be cached by a traditional caching technology. So what are the benefits of using a content delivery network? Well, fundamentally it gives us better performance and improved end user experience for users, especially when using applications which can use multiple round trips that are required to load content. If we think of things like Netflix or video browsing applications, we'll have multiple trips back to the source to be able to load that content and to start streaming it. Content delivery networks also provide large scaling to better handle instances of both high-level workloads and to also be able to cope with peak demands, such as a product launch. Content delivery networks also allow us to use distribution of user requests amongst several servers. The idea being is that we can balance out where those requests are being sent over our network. One of the additional benefits of content delivery networks is as well as storing files, they're also able to store responses to API connections. Quite often in distributed retail and supplier operations, we'll use an API to allow a supplier to be able to contact a partner to query, say, stock levels, information about products and stock results. So what we can do is we can use the content delivery network to record the results of that API command. The idea being that if we're answering the same question again and again, either by issuing particular files or by providing results from an API, we can cache that information around the world and drastically reduce the processing time. Let's talk now about how content delivery networks work. In this scenario, we have a primary user called Alice. She's the first person that comes along and logs into an application, and as part of that application, she needs to access a video file that needs to be rendered in her browser. Because Alice is the first user to request this, her request goes to the point of presence, Now, the point of presence can see that it doesn't have a fresh copy of that video file. So it goes away and requests the information from the origin point, downloads it, and caches it at the edge server that the point of presence provides for us. Alice then gets her video file from the edge server. However, when subsequent users in the same region as Alice come along and request the same information, let's suppose they want to open the same graphics file or video file, their request gets handled by the edge server directly. It can see that it has a fresh copy of the data in there that it can issue out to those users without having to revert back to the point of origin. Now, one of the things that's very difficult to handle here is making sure the information or the files we're producing are fresh and up to date. That's why content delivery networks allow us to assign a time to live value to the various files and query results that we're going to be caching. That time to live value says how long a copy of that data will reside in the point of presence. What that means is the longer we leave that point of presence in place, the longer we leave the data in place with a high time to live value, there's a chance that information could have been updated. So you need to plan in your content delivery network what's the right balance of having a long time to live as a response of keeping that data fresh and updated periodically. As you can see, there are no labs specific to import and export scenarios. However, what I have done is added in Lab 2A a lab exercise where you create a content delivery network and integrate it with your service account. So, now let's take a move on to Objective 2, Lesson 3. Here we're going to take a look at Azure's capability to provide file storage that's presented by an SMB mount point. It'll also provide us with some experience around Azure file synchronization that allows us to provide a distributed file system between the cloud and on-premises systems. To pass the AZ-103 exam and to become certified as a Microsoft Azure Certified Administrator, we need to be able to demonstrate strong knowledge and capabilities in configuring Azure files. That means we need to be able to create a file share in a storage account. We need to be able to create a file synchronization group and a file synchronization service. And finally, we need to have some experience of troubleshooting Azure File Sync as a service. Let's quickly recap on what we explained about Azure Files in the AZ-900 course. Azure File Storage implements 4 tiers of organization and structure to a storage account that stores Azure file information. First of all, we have the account level. That is the object that's created in Azure. That is where we determine where files physically live, the performance tier, and if there's a replication technology associated with that. Within the storage account, we can create multiple share containers. Each share acts as its own file share. Then, within each share, we can divide a share up into multiple directories, just like folders on a Windows file share. And then naturally, each folder or directory contains individual component files. Azure Files offers us a fully managed file share in the cloud service that you could call an infrastructure as a service file share. So one of the benefits of using file shares is that we use server message block to access the contents, and that can be done over the public internet, or it can be forced to go over a private network. Azure file shares can be mounted concurrently by cloud and on-premises deployments of Windows, Linux, and Mac OS. That means if you've got any one of those 3 types of machines, you can access the file share by mapping a drive to it. Azure file shares can be cached on Windows servers using the Azure File Sync role for fast access. What that means is, just like with a content delivery network, we're caching file content close to where the users are. Here in this case with Azure File Sync, that cache of data is on a Windows file server that presumably lives on-prem close to where the users are. There are several reasons why and how we need to use Azure file shares. The most consistent of them is that we have applications or users that are just used to working with file shares, and we want to be able to implement those file shares without having dedicated servers and the configuration and administration required to look after those servers in place as well. Try and think of Azure file shares as a bit like being a file share as a service. It doesn't have a server object behind it. It doesn't implement an NTFS partition on the data, but it does allow us to be able to remotely connect to a file share using the SMB protocol. There are a lot of benefits to that. The first one is shared access. I can grant access to people from wherever I like to the files we've kept on the file share. We do that by either giving them a single access signature, or we can give them a primary key to allow them to have access to the entire file share itself. Azure file shares are fully managed. That means we don't have to look after the operating system of a Windows server if we're just going to implement a file share from there. That can make life easier to operate and administrate the solution. We're able to use PowerShell and the Azure command line interface to be able to configure and automate options within Azure Storage. That comes in really handy when we need to create several instances of storage or manage them consistently. Resilience. Azure Files has always been built from the ground up. However, we can use them as a way to replace on-premises file shares. That means we no longer have to wake up to deal with power outages or network issues on premises or with servers that live on-prem. And also as well, because we're using the SMB as a mount point for this data, we've got familiar programmability. That means the way we integrated our applications with a Windows Server file share are still the same way we integrate our applications into an Azure file share. Creating an Azure file share is a fairly straightforward process. The first step to that, if we haven't done so already, is to create a storage account. Then within that storage account, we go to the services section and choose to enable files containers to be created within that storage account. Just like with any other type of storage, when we create the storage account, we need to be mindful of physically where it's residing in the world based on its region, which resource group it's a member of, because that could determine who has role-based access rights to access it. And also as well, we'll configure performance and replication patterns when we create the storage account. If we have an existing storage account and maybe the location or the performance standard or the replication tier doesn't match what we want to do with the files we need, let's create a new storage account. When we create a file share, we create the file share inside the storage account. It's important that we create a name for each file share because when we access the contents in there, we need to be able to browse the share structure or to be able to connect to an individual share on its own right. Each file share has built into it a quota as well. That way what we can do is apply a limit to how much information users can keep in a given file share. Once we click the Create button in the Azure portal, it can take maybe sometimes a minute or 2 minutes for a file service to appear. That's because there are a couple of additional activities that need to happen underneath the hood of Azure to make it appear. You may want to use the refresh button in the file service view and make sure that the new file share instance that you created appears in that screen. At this stage, we've got a file share object that's available. We've implemented a quota to it to prevent it getting too large for us. What we need to do now is to be able to manipulate the structure in that file share. We can use the Azure portal to be able to do several things. The first thing is we can unload individual files and groups of files into Azure. We can upload an individual file, or we can use the upload button, or we can use the add directory folder to copy a folder that my local machine has access to into Azure. We can also modify the quota that's on there and amend the properties of the file share itself. The most powerful button on the screen though is the connect button. Just like the connect button on a virtual machine will give you a settings file that you can use to connect that virtual machine using RDP, the connect button on a file share will give you the parameters and the net use command you need to run on your workstation to create a map drive to that file share. Within each file share, we may need to create a structure of directories. One common use case for a file share might be a user share. Within the user file share, we might have one folder for each individual users, where perhaps we create their Windows Windows 10 user profile. Maybe we create their document folders in there as well. Maybe we create a project-based folder, a directory with potentially multiple directories beneath it. So perhaps I create a directory called Azure Implementation Project. Within there, I create subfolders called Design, Project Accounting, Change Management, Project Planning, Test Results, and I can then create that structure underneath there. Then individually, I need to populate that with the individual files. Now I can just do that using the storage, using the map drive connection into the storage, or maybe I want to create those folders using the Azure portal, using the screen on the right hand side. Now that we've created an Azure file storage container and made it available, it's time to take our client machines, connect them to that network, connect them to the resource, and to mount to it. So we follow this process on a Windows computer. What we do is, once we've created the file share, we then use the Windows Explorer utility to map a network drive to it. Also as well, we can use the Azure portal to give us the netuse folder, the netuse command that includes the fully qualified domain name and path to the resource, and the storage account and the account that has access to it to connect to it. As we can see, once we've done that, we then need to tell Windows Explorer what drive letter to assign to that Azure file share. And again, we can provide different options like, do we bother reconnecting at logon? Yeah, when we connect to it. Do we want to make sure we use a separate set of credentials to access that storage account as well in that map drive instance? SMB file shares require port 445 to be able to communicate. That means our workstation must have end-to-end connectivity over port 445 from their network card all the way to the storage account. That means we may have to do some configuration of Azure virtual networks and gateways to allow that power to connect outwards. Similarly, on-premises routers may well block port 445 connecting to the public internet, and it's entirely possible that the Windows client firewall on a computer may prevent that connection. There are separate processes to follow on Mac and Linux systems, but essentially they follow the same set of rules and we're providing the same set of configuration. As part of the process of mapping the drive, it's vitally important that we authenticate. Just because we've chosen to publish that information from the public cloud doesn't mean to say we want everybody being able to access it. So we need to provide a username and password pair to be able to authenticate to access that map network drive. We use the name of the Azure storage account that we created in Azure with the prefix Azure / as the username. Then the password that we enter is the storage account key. Remember, when we're giving people access to a map network drive, we're giving them the ability to potentially create files in there, to delete files, and to create folders in there. So when we grant them access, we need to use a key to access that rather than a SAS token. One of the benefits of Azure Storage is that we periodically create backups or snapshots of that folder using the Azure Backup service. If an end user traditionally wants to get a file back from a previous version or to undelete something that they've deleted from their file share, that used to require them to ring up the help desk and to lodge a service request. One of the things Microsoft has been quite good at doing is creating something for Windows called the Previous Versions Client. Back in the days of Windows XP, that was a standalone installer for the operating system. But since XP Service Pack 3, that's been included, since XP Service Pack 2, the Previous Versions Client has been built into Windows. What that means is if I look at a map network drive, I can look at the properties of a folder or a file or a drive itself and see the Previous Versions tab. And in there, Azure will populate all the available recovery points where I can go back and get my data from at a particular point in time. That means we've got a mechanism of providing self-service user recovery. We complement Azure File Service with Azure File Sync as a mechanism to provide a globally scaling distributed file system. This is an alternative to distributed file system that Windows Server provides. So for example, what we can do with file sync is we can deploy multiple file servers either in our on-premises environments or even potentially in our Azure virtual networks as well. What happens then is users will map a drive to the file share, and then that file share they will access will be on their local server. However, what that server does is just keep replicas of frequently accessed data from the Azure file share locally and cache that content. We can use the Azure File Sync service to build out a cloud tiering platform. What that means is data that's less frequently used gets stored in the cloud. Data that's more readily used primarily gets stored on the file server. All data though is backed up though, because when all data is committed, a full copy of it is kept in Azure. When we come to configure a Windows server to run the Azure File Sync service, we have a little bit of work to do. There are some prerequisites that have to be met. First of all, we need to have already created the Azure file container in our storage subscription. Then, we need to make sure our file server is running at least Windows Server 2012 or higher. The Azure PowerShell modules need to be installed on that server. A word to the wise, when you install a Windows server, the PowerShell role can be enabled using roles and features. However, that doesn't necessarily guarantee that the Azure PowerShell modules are going to be installed in the PowerShell service. So it's entirely possible you'll need to write a command in PowerShell to have it connect to Azure, authenticate against the API, and download the latest versions of the Azure PowerShell modules. That will then allow the PowerShell components on the server to be able to interact with Azure services. So, built into newer versions of the operating system, the Azure File Sync service has a GUI built into it where we just choose which Azure subscription our storage account lives in, the name of the resource group that's in there, and the name of the storage synchronization service instance we want to replicate data from and keep a local on-prem copy. The process we need to be aware of for the exam, though, is we need to know how to prepare the Windows server to run the Azure File Sync service. That means making sure it's got PowerShell, the PowerShell modules, and a file subscription already exists. Then we deploy the storage sync service. Now remember, newer versions of Windows will have that built in. Older versions, 2016 and previous, will not have it installed. We also need to install the Azure File Sync agent. We need to register the server with the storage and sync service using the dialog box that we can see here. Then we create a synchronization group and a cloud endpoint that will allow us to replicate the data and confirm which servers certain bits of data get replicated to. Then we create a server endpoint. And then finally we configure network and firewall settings on our virtual networks and potentially our on-premise environment to allow port 445 to flow between servers and the cloud and clients and the on-prem services. Now that we've registered our on-premises server with the Azure Sync Cloud service, it's important that we now create a synchronization group. Synchronization groups allow us to treat certain on-prem servers the same. What that means is we can create a sync group that contains the properties of a synchronization job that determines what data gets synchronized to that file share. When we're configuring an Azure file share to synchronize, there are two components we need to be concerned with. The first is the cloud endpoint. A cloud endpoint is essentially a pointer to where the Azure file service is in Azure. It's a URL, if you like. All server endpoints will synchronization with a cloud endpoint, making it the cloud endpoint the hub of the solution. The storage account for the Azure file share must be located in the same region that we've chosen to deploy the Azure storage sync account. Those two roles must sit closely by one another. The entirety of the Azure storage share will be synced with one exception. A special folder is created that's called System Volume Information. So that folder will not be synchronized. Essentially, that system volume information stores information that's proprietary to the NTFS volume type, which isn't used by Azure Storage. so we don't need to replicate that information. It just gets ignored. Synchronization groups allow us to control the content and where they're replicated to. So a sync group defines the synchronization topology for a set of files. Endpoints within a sync group are kept in synchronization with each other. So if I create a sync group and add 3 servers to it, I'm basically grouping those servers together to have the synchronization occur between them. A sync group must contain one cloud endpoint, which represents the Azure file share and one or more of the server endpoints to allow these devices to connect. A server endpoint represents a path on a registered server. Servers can have endpoints in multiple sync groups. We can create as many sync groups as we need to appropriately, depending on our desired synchronization topology. There are a couple of different ways in which we implement file sync, and that can depend upon the client computer that needs to connect. In all instances, we need to be able to create a file sync group and a file sync service, but there are different sets of troubleshooting guidance provided for client-side troubleshooting. So for example, there's one set of guidance provided by Microsoft to troubleshoot Azure file shares from a Windows server, and a separate set for accessing Azure file shares from a Linux device, and again, the file service configuration as well. I've included the URLs here of that troubleshooting information. Because that information can vary quite quickly, it's worth your while going and taking a look at the steps involved. And from there, you'll see the common error types that can occur synchronizing from a client to the Azure file service and how to treat each one of those scenarios. In Lab C of Objective 2, we're going to get some hands-on experience configuring Azure storage accounts that will run Azure file services. We'll also get some hands-on experience deploying the Azure file synchronization service as well. The exercises contained in Lab 2C basically consist of creating Azure files containers. What we'll do is we'll use Windows Server to be able to create a file share. We'll then create a file share through the Azure portal. Because we need experience with both PowerShell and the command line interface commands to create an Azure file share, we'll also do that from both of those environments. One of the other scenarios you might be expected to know for the exam is how to create file shares in Storage Explorer, so we'll gain some hands-on experience with that. Then finally, in the last exercise of Lab 2.C, we'll extend Windows File Services functionality with an Azure File Sync group. One of the many great misconceptions of the cloud is that backups are handled for us automatically by the provider. That's not true. What Azure does provide for us is a mechanism for us to implement and configure our own backups. However, the responsibility for backing up and restoring data lies with us as the consumer. To pass AZ-103, we need to be quite familiar with implementing Azure backups. That means we've got to be able to configure and review backup reports that give us information on how our backup and recovery operations are performing. We need to be able to perform backup operations where we back up virtual machines, individual files, or databases. Also as well, we need to be able to create a recovery services vault that will help extend backup features into multi-site failover. Then we also need to be able to create and configure backup policies and to be able to perform various types of restore operations. To quickly recap what we learned about Azure Backup in the AZ-900 module. Azure Backup provides 2 sets of functionality. Azure Backups allow us to create standard Azure backups. The idea is there we can back up virtual machines, we can back up files, we can back up applications. They could be running on platform as a service, they could be running on infrastructure as a service. We can also extend what we do with Azure Backup by deploying the Azure Backup agent onto computers that are on premises and use that as an enterprise backup solution to back up data from on-prem servers to our storage vault in Azure. Azure Backup also provides us with Azure Site Recovery Services. Because we're already backing up and replicating data of backups of our virtual machines and their virtual hard drives, it's then very easy for Site Recovery Manager to complement that with some monitoring and automation technologies that'll implement automatic failover of workloads from site to site, cloud to cloud, or from site to cloud. The key component of Azure Backup Architecture is the Azure Backup Vault. That is a software service offering that you create in one Azure region. Because that service is built into Azure, it has access to our virtual machines and PaaS applications through the Azure Fabric. It's able to take backups of those things directly from the storage infrastructure that's provisioned into Azure. We can enhance what we do with the Backup Vault by installing the Azure Backup Agent onto our virtual machines in Azure. That will allow us to create granular file level backups and to also backup instances of SQL Server running on virtual machines. Another form of extending Azure Backup is by deploying an Azure Backup virtual machine on premises. What that will mean we can do is that we can back up our virtual machines or physical machines on-prem by deploying the backup agent and having them send their information to the Azure Backup Server. A short amount of historical backup data will be held there, so recovery operations can happen locally. But ultimately what we're doing is then replicating that information from the Azure Backup Server and positioning it into the Recovery Services Vault. We don't have to deploy Azure Backup. If we've already got an investment in the Operations Management Suite or Microsoft System Center CALs, what we can use is we can deploy an existing Data Protection Manager, System Center Data Protection Manager server, have clients back up using the DPM agent to the DPM server, then add Azure Backup Vault as a lower tiered storage and archival point in Azure. It's also possible to use connectors that will allow third-party software, such as the backup softwares provided by Commvault, Cohesity, and Veeam, to integrate their storage appliances and their storage agents and use Azure Recovery Services Vaults as the cloud-based storage for those backup technologies. For the exam, it's worth remembering one differentiator between using DPM on-prem and using an Azure Backup appliance. Obviously, deploying DPM requires us to have Data Protection Manager agents. That can add to the cost of this. One of the few scenarios you will gain by having a DPM server, however, though, is the ability to be able to support backing up to tape. By itself, Azure Backup is purely a backup to disk and backup to cloud capability. There are a number of backup reports that come out of the box with Azure Backup. They get us to have a look at the performance and success level of backup and recovery operations. They also give us some performance objectives around failover and backup job performance times. During the labs, you're going to browse through the Azure portal and take a look at some of these reports and get a feel for the data it provides. There are several backup operations we need to be able to perform using Azure Backup. The first of which is using Azure Backup to protect a virtual machine. To do this through the Azure portal, we would go to either the properties of the Azure Backup or to the properties of the individual virtual machine and enable backup from there, and either attach it to an existing backup policy, or if we like, to create a new policy that applies only to that server. Whilst an Azure schedule exists for when to perform backups, it's entirely possible that we might want to start a backup job immediately. Maybe because we're about to perform some sort of administration on a virtual machine and we want to make sure we've got a full backup before we start doing anything with the machine. So, when we browse the properties of an individual virtual machine, we go down to the Settings tab of the Management Blade. We can click the Backup blade. Within there, we have the ability to actually trigger a backup or a restore of the VM, or a granular file level backup, or to use the Stop Backup button to suspend all backup operations on that virtual machine. When we create a Recovery Services Vault, there are 4 key bits of information we need to provide. First of all is a unique name for the Vault service itself. Then we need to choose the subscription that we'll use to pay for this Vault service and the consumption it uses. Also, we need to choose which resource group the recovery services vault lives in. I'm a huge fan of having recovery services live in their own resource group. That way I can use that as an administrative boundary to delegate access to recovery services to individual groups of users. Also as well, when we create a vault, it needs to reside in one geographical vault, in one geographical region. If we're going to create a vault to protect virtual machines, our vault has to live in the same region as our virtual machines. Once we've created our vault, we'll then need to create a backup policy. Backup policies are used to identify which virtual machines or file shares we're going to back up, and to choose how long we're going to retain information for and how frequently we're going to synchronize that data. If we're going to use the Azure Backup Vault to create a failover operation, we could use the replicate option to replicate the data from the backup to a remote region. Undertaking a restore operation is quite simple. There are a couple of options we need to do though when we say that we want to restore data. We can trigger a restore operation by going into the vault and choosing a particular recovery point for a particular workload, or we can look at the properties of a virtual machine or a storage account and say we want to restore that data from a particular point in time. Because we're archiving data off, we get a history of restore points, which is a time and date at which we can get the data back as it was at that point in time. In the second page of the restore wizard, we're going to tell Azure how we want it to handle the data restoring back. So for example, if we were recovering a virtual machine, we'd have the option to create a new instance of that virtual machine and spin it up, and maybe we put it in an isolated network to make sure it doesn't affect the production instance of that server. Or what we can do is just have it replace the existing virtual machine and overwrite it there. Azure provides excellent and easy to use configuration. That makes it the ideal platform for backing up virtual machines and storage solutions running in Azure. Because it's so easy to use, a lot of organizations are quite keen on having a hybrid backup solution that uses Azure Backup to not only protect their virtual machines and workloads in Azure, but to also be able to protect workloads that are on premises as well. So, if we have an existing Azure Backup Vault, what we can do is enhance that by going into the portal and downloading from there an image of some installation software that will create an Azure Backup server on-prem. We'd need to install a Windows server on-prem as usually a virtual machine and give it some amount of storage to temporarily cache our backup data. Then we install the backup server role on there and configure it to be registered and use the Azure Backup Vault as its main storage account. Then what we do is deploy the Azure Backup agent to other virtual machines and physical hosts on-prem, and what we can do from there is have those machines' backups being cached to the Azure Backup server. Again, as we said earlier on, it is possible to integrate Azure Backup with System Center Data Protection Manager, but you have to bear in mind that DPM does come with costs, not only from a client per agent perspective, but also as well the cost of having a DPM server itself. Not so much from a licensing perspective, but from being able to have some storage capacity there as well. One of the few benefits that DPM provides over and beyond what Azure Backup and an Azure Backup Appliance server will give us is the ability to be able to record, to be able to back up data to tape and to virtual tape. Azure Backup can't do that for us. In Lab D of Objective 2, we're going to do some implementing and configuring of Azure Backup services. For Lab 2D, we're going to do creating a backup. We're going to do this in several ways. We're going to create a backup from the Azure portal to back up a virtual machine. Then we're going to use a PowerShell commandlet to trigger a backup of a virtual machine and the command line interface to back up an Azure virtual machine. Quite often when we're configuring backups, that's something we want to make sure happens to all of our servers or to an entire batch of servers at a given point in time. It's quite important for the exam that we're prepared to create an Azure ARM template based on a backup job and be able to use that backup template to back up several virtual machines. Also as well, we need to have some hands-on experience of certain restore operations. So what we're going to do there is we're going to do a restore of a disk, restore individual files, and to be able to back up and restore SQL Server running on Azure virtual machines. Then, one of the other advanced backup scenarios we're going to do is we're going to create a backup of an Azure file services share. We're going to create a backup for a Windows Server on-prem server, and finally we're then going to restore files to an individual. So that brings us to the end of today's theory content and to the end of the lab briefings.